Hello guys, I hope everybody is fine. Now, in this video, I'll be talking about the working of a transistor, or we can say action, or working of transistor. Now, if I go back to the transistor, this is my transistor, and it has a it has a base, it has emitter. Let us assume that we are talking about NPN transistor. So this is my N region and this is N and the base is P. So here we have majority of electrons and minority of holes. Here we have majority of electrons and minority of holes, and here we have majority of holes. Now we can see that we have an NPN transistor, right? And as I said that this is, if I put it like this, we have emitter here, and here we have the base, right? So this emitter base should be forward biased, and this is my collector, and this collector base should be reverse biased. So in order to make this emitter base forward biased, I should use positive, I should use negative for this N, and positive for this P. And similarly, the output circuit has to be reverse biased, and so I want to attract these electrons, so this should be positive and this should be negative. Now what we have here is we can think of a microammeter here, and that microammeter will give us the measure of the base current, and we would like to have a milliammeter here. This milliammeter will give us the measure of emitter current. So this is my emitter, so the current I will have here is emitter current. Okay, so here I would like to have another current meter, and that will give me current in milliamps. So this will be my collector current. So this is how it looks, an NPN transistor, and this is its input circuit. This is the input circuit, and this one is the output circuit. All right. So this is this is the NPN transistor that I'm talking about. Now, what I said earlier is that when this emitter base junction, here we have a junction. Okay, here we have a junction, and we call it emitter base junction. This has to be forward biased, and electrons in majority carriers in the emitter, they are repelled by the negative terminal of this battery, right? And towards the base. So the electrons will be repelled into the base. The barrier potential that it has between the emitter and base of emitter and base junction decreases. And the electrons enter the base, right? It's nearly about 5%. I mean, 5% of these electrons combined with the holes. They combine with the holes in the base region, resulting in small base current here, and that can be measured by this current meter, right? And that is IB here. Okay, so I'll call that IB. The remaining electrons, so nearly 95% of electrons they enter into the collector region, right? Because they are attracted towards they are attracted towards the positive terminal of the battery. For each electron entering this positive terminal of the battery, uh, this is this voltage is this is collector based VCB. Okay, so this terminal is the VCB terminal here, and for all the electrons that are entering to this positive terminal of this VCB, an electron from the negative terminal of the VEB enters the emitter region. Okay, so you have an electron entering here, and at the same time an electron leaving from the negative terminal of VEB. So this must be voltage across emitter and base terminal, right? Thus, there is continuous flow of electrons from the emitter to the collector through the base. So this process begins and goes on and on. I mean, the emitter current is more than the collector current, and that's quite obvious because some fraction of current is lost at the base, right? So the base current is the difference between the emitter current and the collector current. So the base current should be the difference between these two currents. Okay, and at the same time, it's proportional to the number of electron hole combinations in the base. In the base of this NPN transistor. So we can note down here that this emitter current is equal to base current plus collector current. So this will give us the currents. But since this IB is very small, its magnitude is very small, so we can approximate this emitter current with the collector current. So we would like to draw this in a circuit form. So the same analogy has to be applied to PNP transistor. All we have to do, all what we have to make sure is that the input circuit of that PNP transistor is forward biased and the output circuit is reverse biased. So the polarity of the batteries has to be set in such a way that the input circuit is forward biased and the output circuit is what should I call as reverse biased. So I would like to dig this pot into a circuit symbol for this kind of configuration that we have talked about, right? So what we have here is we have a transistor, okay, and this transistor is an NPN transistor. So what is the necessary condition for the NPN transistor in terms of the symbol is that the arrow that we will have, let me assume that it's like this is the base and this is the collector and this is the emitter. At the emitter side, if the arrow is pointing like this, so this is an NPN transistor. So we have here a terminal, and we have a milliammeter that measures the current, and then we have to make this input circuit as forward biased. So for having it for forward bias, this terminal has to be negative and this terminal has to be positive. So this will give us the microammeter current because this current is very small, and this will give us IB and this will give us the measure of IE. And then from here we have the collector, right? So this is my collector, and here I have another ampere meter that measures the current in milliamps, and we have to set the output circuit in such a way that that the PN junction here is reverse biased. So in that case, the polarity of the battery should be like positive from this side and negative from this side. All right. So here we have VEB. This is voltage across. It should be VCB, a voltage across collector and base, right? And here we have VEB, that is voltage across emitter and base. So this is the circuit formulation of this transistor in action. And I have tried to explain the mechanism of flow of current due to the majority charge carriers in this PNP transistor. And what is important here is that the input circuit should always be forward biased, and the output circuit should be reverse biased. At the same time, a question arises in our mind that why is it that this base of this transistor is very thin and lightly doped? To answer this question, I think the majority carriers that we have, if we have a transistor like this, suppose this is N, P, and N. So the majority carriers in this case, from emitter point of view, are electrons from the emitter region move towards the collector region through the base. Okay, they move through the base. Now if the base region of the transistor is made thick, if it is sufficiently thick and heavily doped, then most of the majority carriers will combine with the charge carriers in this base region while passing through it. Hence, only a small number of majority carriers that are coming from this emitter will reach the collector region. As a result, the output or the collector current will be decreased drastically, considerably. Therefore, the base region of this transistor is made thin and lightly doped, so that minimum number of majority carriers that are passing in this NPN transistor through the base gets neutralized, and large output current is available. Now, at the same time, in a transistor circuit, we have the reverse bias. This is high as compared to the forward bias, and this reverse bias is kept very high as compared to the forward bias, so that it may exert a large attractive force on the charge carriers to enter this collector region, okay, to have large collector current without getting diffused into the base region, right? So this is we can translate the same thing in terms of PNP transistor. All we have to do is to make sure that the input circuit, this is the input circuit here, and we can see that the base is common here. Base is common between input and output circuit. Now what we have to make sure is that the input circuit should be forward biased and the output circuit should be reverse biased. And in order to make these things happen, we have to set these bay trays in such a way that the input circuit is forward biased and the output circuit is reverse biased.